Awesome. Welcome, everyone. This is another fun adventure with Deep Learning Adventures. We're a fun, engaging community with members all around the country and all around the world. We're excited to see you here. As a reminder, all our sessions are recorded and posted on YouTube, where you can have a look later. Joined by my great friend Dimitri, co-founder of this community, and Robert had some connectivity issues. Hopefully, he can join us later. But I'm glad Dimitri, Vladimir, and Ralph are able to join us today. Small group, so hopefully we can have some interactive sessions and talk a little bit about some of the interesting topics that we're covering. So as a reminder, we are covering this TensorFlow data and deployment specialization from Coursera and Deep Learning AI, led by Lawrence. We have covered how to deploy models on Android and iOS devices, as well as a browser with tensorflow.js, as well as how to deploy models on edge devices like Raspberry Pi or microcontrollers with TensorFlow Lite. And for the last 2-3 weeks, I think, we've taken a deeper dive. This is the longest course by far that I've seen so far in deep learning specialization, where we are looking at the ETL side of deep learning, as well as getting data that are already published in TensorFlow Data Services, tfds. How do we create input-output pipelines? How do we get our data? How do we process them? How do we load them into our model? And today we're going to cover this part where we are looking at bottlenecks in the training process and what tools do we have to look at that and how do we mitigate those. And David will share with us how do we publish our own data sets in TensorFlow Hub, which is basically a library that you can share with others around the world. That will conclude course 3, and we'll take a break next week. We have a happy hour. Again, you can find us on Meetup under Deep Learning Adventures. And after that, we will resume with course 4 and hopefully finish this nice and interesting specialization. So as a reminder, all our sessions are recorded and available in our YouTube channel, and you can find it here on our Meetup page. So as you can see, we've broken our different topics into multiple parts because they're a little bit extensive. So tf.js, Lite, data services. This will actually be the 4th, so I need to update the videos, and then that will conclude this course 3. Cool. So as a reminder, let me navigate a little bit back here, and let me find it. So we have covered, let me make this a bit bigger, full screen, minimize this. So we've covered this interesting notebook from TensorFlow Core Guide, this TF data, which basically takes you step by step on how to build an input pipeline, on basically how to read data from simple data structures. It could be a CSV, it could be text, it could be images, and how to do simple operations, and what tools do you have to basically bring data into the TensorFlow environment. Cover generators, data types, image data generators, which we've seen in the previous specialization. TF records, that was an interesting session where basically this is highly performing, very, very efficient way of storing data in binary format within TensorFlow in a structured way, though. So you need some kind of dictionary of how is the data layout, where is the, for example, if it's image and labels, where's the image part and where's the label part? So you can decode it and use it later. As well as text. We saw how we can interleave text as well. We had 3 data sources from text, I think 3 translations from Homer, and we could interleave them. So if you want to do some kind of NLP model where you're looking at 3 different translations of the same work, you can do that in parallel. CSV data, structured data as well, Titanic data set here, simple data sets. Different data types. Let's see, this is just a reminder of what we covered last time. Multiple files. In this case, we have a GZ file, tar GZ file that has folders as substructures, and within each folder we have different file names. Then we talked about batching and what that means, and padding in case your model expects a specific input length. We talked about multiple epochs and how your training records fit into multiple batches. Maybe the last batch will have less number of records than the other ones, and how you can distribute that. There are different strategies basically here of you want to keep the batch size the same except for the last one, or you want to change it up on each epoch. Shuffling, what does that mean in terms of the record IDs? Yeah, I think that was about it, as well as doing your own custom Python logic. Whatever you want to do, you can write a method for it and you can apply it as part of your input pipeline. Street names, yeah, we saw that. Time series. So I'm scrolling here. I'm just trying to familiarize ourselves again with what we covered last time. Resampling, and this is just for highly unbalanced data set. So there are two techniques for us to figure that out and work around it. Some checkpoints.
Sorry, would you mind going back to what did you say about the unbalanced data sets?
So so here we're working with this credit card data set, and we've covered this in the past.
Okay.
Let's see. So yeah, 99% of the records are non-fraudulent, and 0.0 less than 1% basically is fraudulent. And we covered two ways of how do we do that. Of basically, we figured out what is the negative record and what is the positive record of non-fraudulent and fraudulent, and we sampled in a way that we kept the two groups together balanced. So we have 50-50%. You can specify this. You can do 70-30, 40-50, whatever you want. But when you sample, you're basically doing pick and replace records of, I want, let's say, a batch of 10 records. I want half of them to be fraudulent, half of them to be non-fraudulent.
Okay, so you're doing undersampling largely. Is that correct?
Sampling, yeah. And this one is, so you need, for the previous approach, you need a data set for each class. There's another option here with rejection sampling that you only need one data set that contains both classes. You don't need two data sets. And this is a data set, a tf.dataset object. So you just need to define this class function, and that is applied on each element. So let's see here. I think there's basically a more efficient way of doing the same thing as above. You specify the target distribution, and it actually expects the initial distribution as well, which somehow you can figure out, 99 and 1%. And it will give you, again, if you do 10 records, it should give you more or less balance. These are the labels, a balanced data set. So like 4 or 5 of them are ones, 4 or 5 of them are zeros, fraudulent or not fraudulent. Cool. Yep. So today, also Dimitri covered this optimized pipeline performance, which was really interesting. I highly recommend you check out our previous recording of what happens when you read data, what happens in the CPU, what happens in the GPU, and how can you optimize your performance. Today, I'll cover a little bit about a new tool that we haven't seen before. It's called the TensorFlow Profiler. And if you used profiling tools in the past, maybe from Python or other programming languages, or application monitoring software, this is very similar to that. And I'll share all the links that I'm covering today here in the chat as well as on Meetup. But basically, this is a tool that was developed internally by the TensorFlow team and used extensively in their Google product. and they decided to open source it a couple of years ago. So I'll go over a notebook that uses this and some of the different sections that it is made up of. So I think the best way is to just take a deeper dive into this notebook. So in terms of libraries, let's see what we're going to need. We're going to need this Tensorboard plugin profile. The profiler is a plugin within Tensorboard. So first of all, you need the Tensorboard installed in your computer. I think it's already installed in Colab, if I'm not mistaken, but there's a way also to install Tensorboard as well. Then you install this plugin and import TensorFlow. We're running the stable version 2.5 here. We're also running on GPU. So if you see here, tf.GPU device name, we have one GPU. We're going to use the tfds, which comes with a bunch of methods and datasets available for us. We're just going to load the classic MNIST dataset with handwritten digits of 0 to 9, and we're trying to classify them. These are images. So we're downloading the MNIST dataset. We're going to download the train and the test set. We'll shuffle them. As supervised, meaning we also need the labels. With info means give us extra information about this dataset. We've seen this in the past of who is the author, what is the structure of the dataset, how many records are there, what is the data type, and so forth. So that will return us a tuple of training and testing records, as well as an object that contains information about the dataset. As usual, before running any kind of model, we want to normalize our input. So this is just a simple function that normalizes the image of casting it into a float 32 and dividing by 255 and returning the label. We apply that on the entire training dataset with map. We also want to batch images in 128 records so that we can do vectorized operations in our TensorFlow model. We also do the same mapping on the test set as well, and the same batch. A very simple non-convolutional neural network-based model. It is a very simple DNN. We're not interested in accuracy or loss here. We're just trying to figure out what is the performance of a very basic neural network here. So we have a sequential neural network. We're just going to flatten the image. Basically, we're going to strip it out from a 28 by 1. We're just going to make it into one large vector of 784 elements. We'll follow up with a dense neural network of 128 units with real activation, and then we are classifying 10 classes, 0 to 9, handwritten digits. So we have a dense layer here with 10 units and activation softmax. This is a classification problem, right? It can only belong to one of these 10 classes. So we're going to use this categorical cross entropy loss function. An atom optimizer with some initial value for it. And we want to track accuracy on our output. So far, nothing new here. We've seen this in the past. The new part is here, where we introduce the callback of how do we track metrics. So we'll define a log directory that will be in our environment. And usually, I've seen all these notebooks, they use some kind of like date timestamp. So you can, when you're looking at different models performance, you can see the date and timestamp as your ID. So our logs basically have the structure of year, month, day, hour, minute, seconds. And then we will create this Tensorboard callback with a log structure. I'm not sure this histogram frequency what does it do? But we're interesting because profiling is such a computationally intensive operation. We don't want to do this for all the batches. So let's say we train this for multiple epochs. We just want to train it from a specific batch to a specific batch. So this is the start batch, and this is the end batch. So we're basically going to do it for like 20 batches. So we have our training set. I'm just going to train it for 2 epochs just for time's sake. We also have a validation test to see how accuracy and model and loss looks like. And most importantly, we have our callback so that we can track within Tensorboard how our model is performing. So out of the box, this overfits tremendously. Again, 90%, 95% accuracy. But again, we're not looking at that. We're looking at performance. Cool. Now the next thing we're going to do is load Tensorboard, and you do that with this magic command. It has this percentage in front of it, Tensorboard, and that will load Tensorboard. And to actually launch it, you need to point it where is your log structure, right? So once you point it, you will see here that I run it only for 2 epochs, and it can, sorry, yeah, zoom out. The loss as well. Maybe I need to rerun this, but on this drop-down menu, what we're interested in is this profile option. You see there are other tools as well that some of them we've seen in the past. We are interested in the profile option. For some reason in this collab, I tried multiple times. I couldn't get that profile running. It's just said to me loading data multiple times. I don't know if this is a bug or something. I'll open a case with the profile team, but when I opened this notebook, it already had loaded a snapshot of Tensorboard with profile open. So what you're looking at here, let me scroll down a little bit, is the profile setup for previously run examples. Let me zoom out a little bit so you can see the entire thing, how it looks like. So we have different sections here. We have, remember here, the timestamps that we had. This is just for that sample. The tools are multiple tools. We're looking at the overview page. There are other tools as well. And the host, in case you're running this into multiple hosts. We just have one host in this example. First of all, we have this performance summary section, which tells you on average from input to inference. So this is training, right? So input to training your model to doing backpropagation. How long does it take on average for each step? And the average step for this is about 2.5 milliseconds. And that is broken down by how long does it take to compile the model, how long does it take to do some kind of input processing, work on your model here, hosting it, and then some kind of device communication, as well as how many, if you're using different precision metrics like 16 or 32-bit, which you're going to see, how much time are you spending using either one of them. To me, this graph here is a little bit interesting, the state time graph, and it's broken down with this color schema here, or legend. So we have compilation, which is the green one. Then we have output, which is the dark one. And it's a bit more. The input, which is the red one here. And kernel launch. And how long does it take for the host, device, and device compute. So you see most of our time is spent in this kernel launch and all others for this specific example. In other examples, we're going to see is sometimes we're like really heavily bound on input. Basically, that means that we're doing some kind of heavy processing or pre-processing on the CPU, and the GPU is just waiting for the CPU to feed it with data. In that case, this red section that is very small here would be the majority of it, and we're going to see it in the next example. A nice section here in the profiler is this recommendation for next steps, where you get some automated recommendations. And you see here, your program is not input-output bound because only 4% of the total time step sample is waiting for input. So you should focus on reducing other time. 40% is spent on kernel launch. So 43 is spent on all others. It'd be nice to see what that all others. And the suggestion that you're not using the 16-bit training. You might want to replace your 32-bit operations with 16-bit. It will reduce your accuracy a little bit, but it will improve performance of training and inference significantly. As well as some other FAQs here and some other tools. So another one is the stats tool that we're going to look at, as well as the trace viewer, which gives you a detailed version of this, and some other resources, which is better performance with the tf data API that Dimitri covered in our last section. In terms of environments, we're running one host, one GPU, one core. And if you want to look at what is taking the longest, 14% of our time is spent in this softmax cross entropy with logit, basically figuring out when our last layer, which is 10 units, outputs 10 outputs, figuring out which one is the converting that into a probability, or figuring out which is the max one. I think that's taking the longest. Iterator get next maybe gets the next data record. As you can imagine, sequential dense metric multiplications for calculating the next layer output, or metric multiplications. Bias add gradient multiplication. So doing some gradient calculations as well, calculating softmax again, and so forth. This is just showing the top 10. It doesn't show you everything. So this is just an overview of the profiler. Another interesting screen that I wanted to share with you is under these tools. If you go to Trace Viewer, I don't know if this will work for me, probably not. Yeah, for me, just stuck in loading data, but I have a screenshot here. Let me zoom in a little bit more. You'll see for each device, and we have GPU and CPU, different operations, and basically think of them in the CPU. This is happening, these are different threads, so they're running in parallel. What is taking the longest and where things are taking the longest to operate. So, for example, if I see here, we have a iterator model, private thread pool model, iterator get next op compute, and that is broken down here by individual threads. In some other screenshots that I've seen, it's clearly that one operation is taking the longest and other ones are following up. Here, it's not as easy to see which operation is taking the longest for me. So I'll comment on the next screenshot that we see. So yeah, one thing that we wanted to figure out is how can we improve this performance here that we saw above. Let's see if I can go back. So this launch, kernel launch, as well as this all others. So on average, we're taking about 2.5 milliseconds to do an end-to-end training. Let's see if we can improve that. And there are two changes we will do here. One of them is after mapping and batching, these are the only input pre-processing that we did. We will cache our results. There's no randomization here. We're not doing any shuffling or anything. So this can stay in cache in our memory, in our RAM. As well as this prefetch, while the GPU is doing all the training, we want to prefetch the next data set or the next batch in the CPU as fast as possible with this tf data experimental auto tuning. If you remember again, Dimitri covered this in a previous session. So we'll do that both for the training and the test data set. Again, this cache and prefetch. Train again for 2 epochs. We'll launch again. And I don't see a significant improvement here. Oh, the only thing that I wanted to comment is, this tf data iterator get next. So let me scroll down here. This iterator get next do compute of basically getting the next batch. You see that it's taking, about 22 milliseconds. You want to shrink that, right? We don't want the GPU to wait for the next input. And we're doing that with this caching and prefetching. And if you see now, that became 28 microseconds, right? Like completely different scale. Yeah, you can clearly see it here. This was one use case of how to use the profiler. I have some other screenshots that I'd love to share with you, but I'd open up for questions or comments at this point.
So I'm just thinking about this, and I'm wondering, with time investments, I mean, I would assume it makes one would spend more time on the inference than the training. I mean, I'm looking for input from you guys, where would you focus your time?
So usually most of your time is spent in training, right? You spend hours and hours in training. But
Sure.
when you want to deploy your model in production, you also want to minimize how long does it take to actually perform an inference. And yeah, when you do that, you also want to make sure that whatever pre-processing you're doing, so let's say you are cropping or you are rotating or whatever you're doing, that happens in parallel or as efficient as possible while you are feeding your model with new data.
I think Raf, it also depends on your particular use case. If your AI is frontline customer on your website, you do want that inference to be really fast. But if it's kind of like a back-end process that's looking for fraud or something, you know, the inference part can be slower, right?
I guess it could be, depends on the volumes. When you do batch, you do typically larger volumes of data set, and you typically have windows of time to complete that in. So, okay.
Yeah, that's true.
Yeah, this is another screenshot that the input is, this model is clearly input bound. You see here, it's taking about 30 milliseconds to do training. And you see that the red part, the input part, is taking most of it. Like 83% of the time is basically waiting for input, your model. And you're getting some recommendations here as well. And like caching and prefetching was 2 steps that we took in the previous example. Let me,
George, to Raf's point, I mean, they always, when I always see this, it's always on a training, during training.
mm-hmm.
Can you profile this inference also? Do you also?
Yeah.
I mean, I guess if you run it against the test data set, you're sort of doing that, right? If you're just doing predictions. Could that?
So this is a callback that you call in model.fit, right? Which happens during training.
It's only a callback during model.fit.
I don't know if you can do it in model.evaluate or model.predict a callback. Maybe I need to look that up. That's a good point.
Yeah, they always show it during training.
Yeah, model.evaluate is basically running your entire training or validation set and comparing against your expected labels. And model.predict is actually doing a prediction. But yeah, that's a good question. I can look it up. I didn't see any examples with callback on model.predict because usually you just run a much smaller subset of data. Let me see if I can find some more interesting screenshots for us.
George, I just looked it up. I think you can. It does. The API does support callbacks during predict and evaluate. So
during predict and evaluate, perfect. Okay, and yeah,
so it's probably
possible. You can do those. Yeah.
Okay.
Usually all the notebooks that I've seen is during training because that takes most of your time. But yeah, absolutely. Welcome, Neil. Another great, there was this TensorFlow Development Summit last March. Had some great tutorials. I'm just gonna quickly share with us some slides that I find interesting of capturing data from your profile, optimizing your model, and so forth. So yeah, this session here covers more or less what I said again, the different tools that they have, the overview page where you can see where your model is spending most of the time during training. You can also get a detailed version of it. This is the input pipeline step. There's another one that I like as well, the stats. Let's see. I'm gonna find it. There's a trace viewer. And then they have a simple example of running an image classification with Resonate on a V100 GPU on GCP. And this is their setup, the Tensorboard setup, and the callback during training in model.fit. And let's see what they get. So again, most of their time is spent in input, meaning their GPU is waiting for, so input time is 900 milliseconds for training step. And let's see how they improve it. So they look at the recommendations, right? It's 81% of the time is spent on input. Look at input pipeline analyzer or trace viewer to see where your model is spending most of the time. And if you look at the input pipeline recommendation, you see data pre-processing is taking almost all the time. And there are two things that they changed here. I've seen them all being repeated again and again. One is converting this dataset.map. By default, runs one batch at a time in a sequential manner, but you can do that in parallel by specifying these non-parallel calls to a number. That's number one. And the other one too is this prefetch that we saw before, where you're doing the prefetching of your data as your model is training. So you're doing things in parallel. So yeah, optimization number one, from sequential map to parallel map. And you do that with non-parallel calls is this tf.data experimental auto tune. So let TensorFlow figure out what is a good number of parallel calls based on your host and GPUs. So that shrank. Remember, we had like almost like 1,000 millisecond average time. Now it's 200, like 5x better. And the input is probably not even there. Significant improvement, so 5x speed up. And the other optimization they did is they converted some operations into, or all operations to 16-bit operations instead of 32-bit. There's another session that I looked in on this DF Summit, TensorFlow Summit, that basically said that you can do, if your model was trained with mixed precision. Mixed precision means that parts of your model are running on one, maybe float 32 operations, and parts of your model are running on 16. So for example, if you want to do some kind of weight aggregation or any kind of gradient calculation, you don't need float 32 accuracy. You can just do it with float 16. But your weights and biases, you can keep them as float 32 for more stability and better performance. So if you do that, let's see, I think we got, yeah, almost 10x speed up compared to just using 32 by just converting to 16. So this was last year. I'm hoping they've implemented these features because they talked that you could actually pair this up with specific keras layers and specific keras commands. If you remember when I showed you, it was kind of like very low level, matrix multiplication, sparse cross entropy calculation, and so forth. I think then hopefully by now version 2.5 has this kera specific analysis, as well as if you want to run this on instead of one node, you want to run this on multiple nodes with multiple GPUs. How do you profile that? So this was an interesting session. There was another one that was a demo here. Let me see what was interesting here. Very similar setup here. Let me see if I can remember. So yeah, this is how you call the profiler. You can do it as a callback that we saw. You can also call the TensorFlow Profiler API, which I haven't seen yet, as well as this sampling mode where you decide when your training is happening, I want the profile to run between this batch and this batch right now on demand. This one is more like you specify in advance from which batch to which batch you want to run this. Yeah, let me see here what changed. Again, you see a lot of input and all others. Data pre-processing, that's most of your step. And in here, you can see a breakdown of like computation, get the next data set, and so forth. So again, he changed this from sequential to parallel mapping, caching the data as well as prefetching, and that gave him much better performance graph here. Yep, and last one. This one was a good one. Scaling TensorFlow data processing with TF data. So you have data pre-processing happening on CPU, and you have your model computation happening on GPU or TPU. What is happening is that GPUs are becoming so specialized in doing vectorized operations that they can do more and more in parallel, where CPU is kind of having a hard time keeping up with feeding our GPUs with data. So that's why this TensorFlow team introduced this tf.data pre-processing framework and the different tools that we've seen. So one simple example, getting rid of from TF record. You have some kind of expensive pre-processing step. It could be image augmentation if it's image. It could be some kind of calculated fields if it's structured data. It could be anything. If it's text, you name it. You map it, you shuffle it. Again, you don't want to show your model the same data in the same order, right? Otherwise, you might learn some kind of order in your training. You batch it, you prefetch it, and then you have your model and you fit. So this is the basic pipeline. This does okay, but the internal team in this is called the TensorFlow performance team within TensorFlow figured out, wait a minute, if you're doing this kind of expensive operations, if there's no randomization in them, can we store them somewhere? Can we cache them somewhere? So that was our first idea of, we have an input data set, this computation before, have we done it? Yes, read it from disk or RAM. If no, compute it, store it to disk or RAM, and let's keep it there. And yeah, so this snapshot is called tf.data snapshot, where you compute once and use multiple times. That was one improvement that they introduced. This is, I think, in TF 2.2, so I'm pretty sure it's still available in 2.5. And how do you use this? You introduce this dataset.snapshot and you specify a path. And the order is very important here. You see here where he introduced it after reading the data, doing the expensive pre-processing, then taking a snapshot of this expensive pre-processing. So there's no randomization here, basically. The data is stored in disk or RAM, and it's read if it's pre-calculated. Then you do all the random operations like shuffle and so forth, batch, prefetch, model. So that's one optimization they introduced, available in 2.3. Then the other one is if you have a production environment where you have multiple VMs, basically, right? You just don't have one. And he mentioned that if you just say, okay, I'm going to run this on my own, I'm just going to spin off 3 VMs or 4 VMs, I should expect 4x improvement in my performance, but you're only getting maybe 1.5, and what's going on. So again, the goal here is I have multiple CPUs. Sorry, this is for multiple CPUs. This is not for multiple CPUs and GPUs. How can you use
question for you when you have a chance.
Yep.
Back on that snapshot, my understanding is that dataset.cache by default caches to memory, but you can cache to local storage. Wouldn't that be the same thing as snapshot? I'm confused about what the difference is there.
Yeah, I don't know if this is called cache in 2.5. I don't know. This is also like a year-old video I'm looking, so I don't know. Maybe they renamed it, but to me, the goal is to do something computationally heavy and store it in either memory or hard disk. I mean, this is a path to your hard disk, so.
Yeah, and that just seems like the exact same thing to cache.
Mm-hmm.
Unless the format is optimized in a different way.
Yeah.
The way I think the materialize maybe.
Maybe.
Yeah, maybe. Yeah, I can look at the difference between cache and snapshot. Yeah, maybe. I mean, there's an RFC here, so maybe the format, you're right, is slightly different than cache. Cool. So the other option is you have multiple CPUs. How can we speed it up? You now have this randomized preprocess where you cannot use that cache or snapshot because you don't want to compute once and read the same data again. You want some kind of randomized pre-processing. So basically, every time you run this function, you're going to get slightly different output. So you have your TF record data set, your map, the same shuffle batch, but now you have this distribute command here, and you specify where is the coordinator node of multiple CPUs. And all the commands that are happening before distribute, this coordinator node will figure it out how to distribute them onto multiple VMs and multiple CPUs. So now basically you're distributing your workload on multiple hosts instead of just one. And then they're all coming back to you and prefetching, giving to the model and fitting. So this is basically you are distributing the pre-processing part into multiple hosts. And that's the TF data service. Cool. So snapshot allows reuse of data pre-processing. Service enables distributed data pre-processing. That was the message of this video. And sorry, I said last, but I was mistaken. This is the last one where now you have multiple CPUs and GPUs, and you want to scale it out, and not just the pre-processing part, but also the training part. So yeah, for hosts, you expect 4x improvement. You're not getting that. And he talks a little bit about how to use this multi-machine, multi-GPU setup within TensorFlow. And using this specific example of BERT of an NLP and this squad reading comprehension task of seeing how the performance improves when you go from one host to 4 hosts. And he'll introduce 4 different optimizations. I'm not going to go into detail. One of them is this NCCL, NACL, that Nvidia uses extensively. This is the Nvidia Collective Communication Library. So when you have multi-nodes, and each one of them has multi-GPUs, Nvidia has this protocol that are basically used to do some kind of think of it as in Hadoop, right? Like we do all reduce, all gather, reduce, scatter, broadcast, and so forth between multiple nodes. It's like a very efficient way of doing that. So you do that the tuning, you get a little bit of maybe almost, I won't say double, but less than double improvement. You introduce that mixed precision that we saw before of using parts of your calculations in FP16, and then as well as overlapping some computations that can take place in parallel. You introduce further optimization. So this is, let me show the entire graph here. This is if you have 2 devices, 2 nodes, each one of them has their own GPU, left and right, and you have 2 layers. This is our very simple neural network. We have layer A and layer B. Each one of them has, just for sake simplicity, let's say a set of weights VA, VB, and you want to train this in parallel into 2 multiple devices. So you can run this in parallel. At some point, though, you need to exchange weights, right? You need to make sure that your model is, you're not running 2 separate models into 2 different devices. You're running one model into multiple devices. So you need some kind of weight exchange as well as backpropagation to happen in both at the same time. And you do this and you run the profiler as well to see what is taking the longest. And you see here the forward path, a lot of things happening, the backward path, a lot of things happening. Those are happening in the GPU and the variable updates. But the longest time is in this gradient aggregation network where the 2 devices are exchanging the gradients they computed to each other so that they can be updated. So you see here the blue bar is taking the longest here. So gradient aggregation time dominates the step time. That's the problem here. And not only that, so optimization 1 was this tuning this NCCL, and they have a guide here of how to do that. And they also mentioned at the end that they're hoping to have some kind of auto-tune feature as well so that the user doesn't have to do it, because it's kind of like a manual process. And I think they had a graph here somewhere, but it's basically you try multiple times and you see at what NCCL parameter your training optimization, your training performance works best. but I think by now it should be kind of like auto-tune, where you don't have to figure it out, let TF figure it out for you. The other optimization they did is this converting from gradient aggregation from 32 to 16. So let all the gradients do all the computation in float 16 instead of, sorry, just the aggregation instead of 32. And the other one is this backward path and this exchanging gradients can happen in parallel. So how can we have them happen in parallel and save a little bit of time? So those are the 3 improvements. So this is the manual NCCL setup. And I think they said, yeah, that future work, this should happen in AutoTune. So that introduced this improvement here. Bigger is better. The other one is this mixed precision API, where you are not using a high definition float basically for weight aggregation. Sorry, for gradient aggregation, you're just using a float 16. Let's see where you do that. So they use this gradient tape as tape, right? They really go into the training loop of TensorFlow, which we haven't really used. I mean, you see this in PyTorch, but this is basically the advanced version of how do you run TensorFlow step by step. How do you control the training loop and the gradient, the optimizer, how do you apply the gradients and so forth. So I'm not going to go into detail here too much, but basically you can do a bunch of casting the gradients into 16 float and 32 float, and that gives you a lot of speed up basically. And they're saying that hopefully they can do this as part of the keras compile feed command. So that was a precision update, this step here. And the last one they did was this collective hints. That's a new feature in 2.2, where I think you can specify how many. So let's say you have weights that you want to share from one device to the other, or some kind of parameter. You can do that in packs. You don't have to wait for all of them to be updated. You can pack them and send them from one device to another. That's the update here. And this is the manual step that I was referring to at the beginning. You have to do some kind of calculations to figure out this is the optimum size of my NCCL parameter, like between here and here. After that, I don't see a significant improvement. Yeah, that's what I wanted to share. I'm hoping next time we cover this, it'd be nice if I could have the profiler actually running so we can see some actual results. But this one I wanted to cover, and there's some more videos I'll share with you. But after that, we should be in a good place to analyze this. To take a look at this notebook as well, which takes a deeper look into the different steps. Yep, go ahead.
George, one comment. So I think I have used the profiler on Colab. On Kego, it had some problems. I think I never succeeded to make it work. But I'm using it extensively on my local computer. Now, in order to see right here, the GPU threads, this compute mem copy from host to device and device to host, and things like this. You need some special version of CUDA. And what I remember, I read 10.2 is the minimum. I managed to start it on to use it on 11. So because you know that there is 10 combinations that work. So I was using TensorFlow 240. I think CUDNN 8.0, something like this, and CUDA 11.0. And this combination succeeded on my laptop. And then you really can, I mean, run this thing, you can zoom in, you can see kind of more interesting things when you start looking at the, when you zoom in these things, the functions in each of the threads to inspect actually your code, how because these are kind of, so let's say on Python 3 that where you see, you see like 4 or 5 levels of functions that are being called nested. So when you start yeah, when you start optimizing this, you basically need to zoom and see what happens there in order to optimize your code. So that's my advice. Just get it. If you're running on your computer, I use PyCharm and it's pretty good.
Yeah.
So it's kind of my 2 cents.
Yeah, I don't know if this Colab in the back end, I would imagine had all the drivers you need to make it work. But for some reason, for me, when I go to Profiler, it just sits there and never gives me any data. It just says loading data. Okay, cool. Thank you, everyone. Stop sharing. I'll hand it over to David.
Thanks, George.
Maybe you can just try to, sorry, yeah. Just try to see what kind of code is running behind the, so in Colab, just start some terminal commands, see what code is running, and if it's not, I would say 10.2, that's what I had. Maybe the plugin is installed, but it cannot do much.
Yeah,
Because you
I can
need
show
to
you.
source from CUDA.
I can show you in the end after we stop the recording. Yeah, I'm happy to run the Colab. It's I have it open. We can take a look together if you want. Oh, there's David.
I'm going to go and share.
Okay, that's fine.
All right, I hope you can see my screen now.
Cat versus dogs.
You see it? Okay, great.
Yeah.
So I'm just going to change to a completely different topic. You recall in one of the earlier courses at the start of, I think at the start of this course, week 1, we introduced the concept of the TensorFlow data sets, which has a very large catalog of different types of data sets with different types of all kinds of large and small data sets and many different categories, including more recently they've added reinforcement learning into it. But just for instance, in image classification, you see something like cats versus dog, which was a very simple one. And you see things like in there, you see the description of what the data set has, where it came from. A lot of times you'll see a reference to a academic site where maybe a paper was produced about the data set. Often there's a home page that it's associated with. The versions that are available, many times there's changes in the data set, corrections or additions to the data set, and they'll put out a new version, and you're free to pull whichever version you want for your needs. They tell you how big it is, the size is calculated sometimes, not always, but the download size. Sometimes they'll list what the size is after you uncompress everything. So that can be much larger. They'll give you the predefined splits that are in the data. This one just has trained, so if you want to create your validation and test splits, you need to do that on your own, but often they will have, I've even seen multiple test sets in some of the data. And then they describe the features that are in the data set itself. In this case, it's the image with the shape of it, what type of data the data type that it is, the file name for that, and then the labels, and how many, you often get how many, in this classification case, you get how many classes there are in that label. They tell you, we went through you have an option to pull the data set with supervised keys. So if you use that, you'll get the image and label here, and you won't get the file name. You can see some examples here. They've got that it produces those. You can do that. And there's almost always a citation to where this data set came from. Maybe if it's from an academic setting or a paper, you might get multiple authors, the title of a paper that came with that, or in this case, it was the proceedings of a conference, the year, the month. Various other information. It's a formal citation that comes out. So what they would like to have is, if you have access to a data set that you've produced, they would love for you to load it up into their catalog and make it available, if it's public, to make it available for other researchers and amateurs and experimenters and, you know, deep learning adventurers like ourselves to be able to pull that data down and analyze it and do what we can with it. This grows pretty steadily, actually. For a while, I didn't see it change much, but now there's a lot more data sets being added. Every new release of the tfs.ds, there's a bunch of new data sets being added. So people are obviously taking advantage of that. But how do you do that? So that's what I'm going to be covering. And I captured from the videos, this is an optional section of the class, but I captured one screen that I think is probably the key thing. Every time you create a data set, you're going to create a class, a Python class with a name for your data set. And you're going to basically implement a class called generator based builder. You're going to have in there, you're going to specify your versions, and there's some details you can put in other than just the name. But you have to implement 3 different methods within there. One is info, and there you've got things like a description, the features, the supervised keys, that citation. So it's all of these kind of objects that you see in here, including the citation and everything. You're required to, you know, put that in there, this info. So you've got to implement that. You've got to implement generators for the splits. So here they only had one, but you could have many different ones for the different splits. So that's another thing you generate. And then if you recall, they had those examples. That's what's being done here, where you basically, this is just a generator that yields out different multiple examples. And here, when you hit something like this is what it does. It generates your list of, in this case, I think 10 examples. So whenever you create a data set, this is one of the things that is where you're going to spend a lot of time. So the rest of the course goes through the steps that you take to actually add your data set and put everything into the tfds format and then submit it. And the gist of it is that you will actually capture everything that's here is kept in a GitHub repository, which you will clone and basically create in whichever category you need to your own section in GitHub for those data sets. So each one of these is actually part of the GitHub repository. And once you've added yours in here, whatever it happens to be, you're going to actually do a pull request back to TensorFlow's GitHub repository, and they'll review it and you know, approve it if it meets their specifications. So let's look at the we're going to look at the collab, or the notebook where Lawrence explained how this happens. And the first one we're going to look at, I'm just going to start running it because it takes a little while to run. But okay. So we're going to. You don't need to do this step. It's TensorFlow datasets is now already there as part of Colab, so you don't need to install it anymore. We have a few helper libraries that we pull in, and the data set we're going to use, since we don't just have our own, we're going to use one called Imdb Faces, which is an interesting data set. It comes from this study about IMDb Wiki. They took over 500 different faces of celebrities from 2 sources, the IMDb database you know, data set, as well as a Wikipedia data set of images. And they took those photos and information around those photos, such as when they were taken and the date of them and things like that, and additional data about the subject or the celebrity that's in the photo, such as their date of birth, their gender, name, and some things like that. They have a way of scoring the photos with this detector they made that detects, that it is this celebrity in the image. So the better the look at the face in the image, the higher the score, basically. So that's just an example data set. You can read a lot more about it at this link if you're interested in how the data set was produced. But since it was from a paper, we've got, the authors of the paper, you've got information on them, things that you could build that citation with based off of this information. So we'll see how we use some of this information. Sorry, I was trying to get that back to my screen. Okay. So as I mentioned, you have these kind of features in this data set. We're going to pull it down. Oh boy, it's slow right now. I should have done this about 10 minutes ago. But this part of the notebook is just examining this data set. You obviously want the best quality you can have from this data set. And we're going to learn that we need to pull out certain information. There's a metadata file that comes, so you have a file that has all the cropped images, the file path here, but you also have a metadata file that has a lot of that other data that I was talking about, such as the name and date of birth. And so they talk about how to pull that out and look at that. It turns out that he goes through this where you fill in some of this information in the class. So I'm feel fine with showing this since he showed it on screen. But there are several of these that are going to have some missing information. So we won't have the gender in every case. So there'll be some null values in there. We also won't have, for some of them, we won't have the second face score. So we're going to go through and do some cleaning of those eventually. So let's see down here. We'll see that we're going to first, we're not going to use the celeb names as a feature. We don't need that. And we're going to clean out some of the nulls right here. So he looks at that, and we'll go through and take that out in a minute. Hopefully this is downloading. Almost done. So it goes fast. It'll be fast after this. Installing as much as I can here. Any questions so far? I can't see the chat. So
the labels are gender and age. Is that the concept of this data set?
So we are going to well, we'll start that in a second, but
okay. You can specify your own labels.
Yeah, since this is our data set, we can produce it however we want.
Got it.
All right, we're close. You can probably cut this part out of the video while we're waiting.
Okay.
I was looking for the labels just for a second.
You can choose your own labels. Like that's the whole point, right? You create.
Yeah, if it's your data set, you can structure it
whatever you want. You can
the way you want.
Create calculated fields for your labels. Like I don't know.
Yeah. I just trying to remember. They're going to do that right down here. So I was just jumping ahead just to look for a second. So we're going to supervised keys are going to be gender.
Okay.
So we're going to label whether it's a male or female. They don't have non-binary values in here. So. Okay. All right. So we're past the download. We're now going to look at the metadata that came with it. So that's what's happening right now. Here you can see we've got a lot of metadata. Each one of these files are pretty intense, right? So we've got a bunch of arrays of Imdb data, and then down below that we've got more data around all the other metadata. So we want to be able to pull out all of this and extract it from that metadata file. He goes through how we have to basically do the indices of these NumPy arrays and pull out what we need. So here's kind of what we're doing. So this is basically to help you understand how to pull this information from this data set. Hopefully you would already know this and have this, your own data set. You would already have all this done.
Maybe that
Yes.
pipe O, is that like a missing value? Is that what it was? Like a delimiter for missing value, or
Where is that?
this one, yeah, here.
Oh, the O. Yeah, I'm not sure what the value is.
It's like a missing.
Yeah.
Okay.
So all the values come off the root. You can get their key and then get the first index in the array is the values. So here we're pulling it down to the main thing that we need. You can see already in the second face score some of these NAs that are in there. And then here they're just looking at what are the distinct keys that are in there. So here's our names, here's how the values are gotten. So you can look for, DOB, you would have these arrays. So we're going to clean this up. We don't need all of this data that happens to be from this paper. We're not going to use the celeb names as one of our features. So we're going to cut that out, and we're left with all of these features and these many values. You can see now they're pretty close. They're all the same length. We do have some nulls in here, but we've got this is going to be our features that we're building. We're going to read that into a data frame for a little bit easier processing. That allows us to look for those nulls that I was talking about, or those NAs. And as I mentioned, some of them we don't have a gender for them, or we don't have a second face score. So a large number there. We want to now create a data set for us to use. And the first step in here, what he's going to do is clone the GitHub data set, the tfs.dataset dataset. Now he did this for a very specific version, so that matched up some of the things he was doing. But I think now it's at version 4.3. So it's a little bit different than what you see in this, but this is still pretty close. So here I'm running in collab, so I'm just going to go ahead and do that here. So when I do that, I get over here in my folders, I get this thing called datasets, and it has some documentation and scripting and stuff. But the main thing it has is TensorFlow datasets. And here you'll see basically a copy of what we saw on the website for TFDS, the catalog. So this is an older one. Now they have image and image classification, but back then they just had this image one. And you can see in here is things like CFAR, and MNIST is down here, and the IRIS database, and a whole bunch of different data sets, but they all are represented by a py file. So every one of those data sets, like MNIST, for instance, is a .py. So that's what we just downloaded from GitHub. And what we're going to do is put our data set as a py file in here. So we have to produce that. So so we've done that. We changed over here to look in there. We're in that directory. And one of the things we need to do is produce kind of a skeleton for us to put our data, our py of this py file. So they have a nice little utility. You run Python here, and you're going to run this create new data set, which I was talking about some of the scripts. You give a name for your data set, and you tell it which category, is it going to be an image or an audio-based data set? So you're going to tell it where you want it to fit in here. So that's what this does. It generates that for us. And in there, we can look for statements that say to do and the name of your data set. And that's where we need to make changes in the file. So when we run that, we get, oh shoot, where's it? Sorry. What did he call it? He called it my data set. So we should now see an image. We should see my data set. Did I run it? I don't know where I put this. Data set, you can check.
Is it maybe in the end of the?
No, it's, I can't remember where it's. Let me look real close if it's. No, where is it? It's not an image, it's not in my data set. Did I kill it? Oh no, I don't think I know what it is. Imdb. Yeah, I actually renamed it. Sorry. So it's going to be here. It's this one. This Imdb Faces. And he gives an example of how in Colab or in a notebook you can actually write to a file by using this IPython magic notation of write file and the file name you want, and anything after this in that cell will be written as it is into the file. So, he shows writing that, and then you cat it, and you get what you wrote in there. So just wanted to show how that functionality works. But I mentioned we need to do this file. So we've got this Imdb Faces, and I did find when I ran this that I couldn't do it the way they were doing it. I had to put the full path name to the file for it to work. It wasn't actually, even though we did a change directory up above to this directory, it still was not writing into the right place, and it would say file, couldn't find this file not found. So I made that change. So you have some imports that are standard. You don't have to do anything here. Nothing really has to happen until here. We're going to put in our publicly available data set, description. We're going to put in the URL where this was, our data set root directory, annotation file. These are just variables that we're going to use later. We're just setting them up here. But here's one of the first things we're going to do is create a citation. And he mentioned a nice tool out there called, it's the BibTeX online LaTeX citation, kind of a generator. And if you put in like the author and the title and maybe the journal that it was published, what year it was published, and other information, it'll actually generate down here as you put it in, George Zoto. It'll actually fill it out for you. So you can generate it on the fly and then copy and paste this into your citation here. And so that's how you can easily produce this correct type of syntax for citations.
Cool.
It's a nice little utility. So again, he's just getting the URL. He just set this variable. But I mentioned before that there's a class we have to override this generator based builder, and we have 3 methods that we need to implement for this to work. So here's where we start doing that. So we're gonna have this Imdb Faces class that extends this generator base builder. And the first thing we're gonna do is implement the info method, right? And this is where we put all our information about our data set. We had already put the description above, so we just pasted that in here. We're going to start with our features dictionary. And if you recall, when we're looking at them and processing the data set, we stripped everything out so that this is what we had. We have the image, gender, date of birth, photo, when was the photo taken, the face location within a bounding box, a face score, a second face score, and this ID. And for each of these, you want to give it the type, right? So it's the dictionary, that's the name and the type. And in TFDS, these are the types that are available to us. So this is the features and the different types of things that we can have. Class labels, everything's pretty standard that you might see in the data, sequences. They recommend that you try to be pretty specific. You could put everything as a tensor, but it would not be the best data set. It doesn't tell the end user. We would have to do a lot of investigative work to figure out what the features were if all it said was they were just tensors, right? So you want to help your end users of your data set out and try to put some interesting things here. Things like class labels, you can tell it either the names of the different classes you can put in here, or the number, how many there are, if it's a lot. If it's the names, you just give a list of them. So I could have, maybe done this where I put male, female, because we're predicting the gender, right? But here are just number of classes. The face location is in the photo. Where's the face? And so there you can use the bounding box feature, and I'll show a little bit more about that. And then if you have a supervised keys for this, so they can download them, you would just tell it, I'm going to download the image and the gender. You're not going to get any of these other features when you do supervised keys. And then up above was that URL, that citation that we produced is there. The second thing we have to do is implement split generators. And there's a bunch of different ways to do this. Here's how he did it for this one. He's just, first of all, he's using a utility called Download Manager, where you're pointing at the URL where the data set, the raw part of the data set is. And this just produces a path where you can find the downloads. You can find it downloaded and extracted there. Basically what this gives you back is a path object to tell you where locally, is it downloaded to. Once you have that, you can use that to actually extract some of the metadata and some of the other things. But we're gonna, inside of here, we're gonna define another method for parsing out that metadata file. One thing he does advise is to use, instead of using like some of the more Python file utilities, to instead use TensorFlow's gfile utilities. It works this way. It'll work very well if someone's on a cloud, like on using Colab or something like that, or they're using some of the Google's own cloud services. So we're going to pull the data set here and return this full thing. We can put it in the meta. I talked about, it knows where to look for the file based on these things, based on what the extracted path was with that utility. And we can pull out different, different fields if we need them. So we're going to just create some male, female type of names here, the celebrity names, just showing you how to get some of these info features generated. And once we have all that, we can use that in a split. And the thing we're giving here is just this generator knows, it's smart enough to know that if we tell it where the image directory is and the metadata that you're sending back, it'll work as expected when they do a tfds.load. The last thing we're going to do is implement this generate examples, where we have basically a generator that yields examples. For that, we're going to, sorry, we're not there yet. Sorry, we're still in the split generators. We have to actually generate a few more of the features. So where was I? Sorry. So one of the things we're going to do is another helper that gives us the bounding box values. I mentioned that we're going to return the bounding box for where the face is located, and that's just some taking those annotations that we're giving, coming into the method here and producing these values to return back for the bounding box. We can return, we have an image, a helper here to get us the shape of the image. And then here's one thing that's different. So this is generate examples I was talking about, but whenever we need to call some, how to say it, like other pandas, not, sorry, other Python libraries that aren't part of TensorFlow, we don't just do an import up in the top of the file. We use this thing called a lazy imports, and we can then load our pandas. Like for instance, we're gonna use pandas here, and we'll do it via, we'll import them basically via a command like this. And then here we're building up those features and putting them into a data file. So here we're using that pandas that we had before. We zip up all this DF of this data frame of the features that we've seen before. And we can, if we need to do some pre-processing, like we only want to pass back ones that have a good face score, so images that have a very clear face in them, we can filter the data set. So you can do quite a lot of heavy processing on the data set before you yield it out to the end user. Here, remember we talked about some of the genders were not available, so we're going to take those out. We were missing a lot of these, so we're going to skip both of those. I changed this code a little bit here just to show a different way of doing the same thing. You could do the, where it's not is in A, or you can just go where it's not in A and get this, it has the same effect. We're going to cast genders from into an integer type so that the user doesn't have to do that to create their labels. We're going to go ahead and label it as integers. And then you can go and iterate over this data frame and return the yield all the features back, including gender, right? So your labels in there too. So that's implementing that get generate examples, which was our last part of what we needed to do for a data set, all inside of our class. Okay, so we've done that, and we've written that out to our Imdb Faces.py file. The next thing is to add into each of the categories. In this case, image is an init, underscore init that has, we can just open it real quick to take a look. It has a bunch of imports of all the different classes for each of these ones. So ours needs to have one in here. I can't remember if I put it here. So I added this row, Imdb Faces, import that class that did the override, so the Imdb Faces. So that has to be there. That's what he's doing here. And then you can do checksums also for people to make sure, when they download things, they're getting the right versions and no one's running an attack on them or anything like that. And the last thing to do is run the this command to create, download and prepare that data set. So this runs it locally so that you can see if it's working and be able to then call tfds.load on your local system and download it, because it'll be there. So this builds it out. They did not do it in the collab in the course because it was expected to take a really long time. I tried to do it locally, and for the life of me, I could never get it to work. It would never see my data class in there, and I wasn't sure exactly what I was doing wrong. But regardless, what I should have been able to do after that is load it up. Of course, they didn't do this because of the size. They didn't run it either. But this should have made it available to me if I imported tfds at this point, and I could call load, and it would see it locally and grab it, and then we could explore it. The next thing I did was because I couldn't get it to work, that step, I went and tried on my own, and I want to show you that real quick. I went and read another set of documents that's much more new. They have some ones, a couple of ones. One is here. It's this writing custom data sets here, and the other one is this tfds. Now they have a command line interface that you can run. So I tried using this method, which is a lot newer since I think the course was developed. So you can see the first thing I did was run the command line tfds client. And if you give it the keyword new and a name for your data set, it will stub out and generate what you need for your data set. So I better see if this is still, yeah, this is still available to me. So this one ran and it created my data here in this my data set over here. And what it created for me was that checksums file. This is a dummy data directory, which if you're going to do a test, write some tests against your data set, you would put the data in here for testing. We get init.py. We get the mydataset.py, which is what I called my data set. So this is the one that's important to us. And then you get a stub for a test that you can run against that. So the first thing you're going to do is go into mydataset.py and edit it. So I'm going to open that up just to show you. I've already done the editing. So I want to show you what it first came down. So here in the green, I've commented out, but this is what you initially get is this kind of thing where everything in here that says to do with the name of your data set, you need to fill in. So again, like before, we have to fill in our description, our citation. We're going to have a class that we're going to have to fill out the 3 methods for. You can put version things in here, but remember we have to do our info, our split generator, and generate our examples. So once you implement these 3, you're good to go. And since I had trouble with the collab that he gave us from the course, I went ahead and copied in his horses or humans data set. So I got this from TensorFlow.js, image classification, you know, his one that he made, which is the horses or humans. Yeah, here. So I took this one and just to see how he'd done it and use that for my data set. So so that's where I got this from. So I didn't change too much here. I knew that this would actually be a real data set that it would be able to go and get and fetch and use. I changed the name to my data set. Changed some of the documentation. I didn't change any of this, but you can see it's got just these image and label features. So you got a feature image. All you have to give there is the size of the image, your class labels. Here's an example where they didn't do the number of classes. They actually showed the actual list of the class names. So here we have horses or humans, the keys and the citation and all that. Here's a split generator that he wrote to give a train and a test generator. They come from different paths that he's defined here when he uses download manager based off the URLs. The train and test URLs are defined up here. They're stored on the local GCP storage, and over here are the validation. He's going to call this one test instead of validation, but basically this is your training and this is your validation data. So he's calling it test and train, and he's using those in the generators to get those paths. So that's your generator definition, and then you have to generate the examples. It's pretty straightforward. Basically, looks for the names to match for the PNGs, and it does that. So based on how your data set's laid out, you can generate that. So actually, this is what I use for my data set definition. So I edited that. I changed over to this directory. And the next thing I was supposed to do was run from the command line tfds build, and it should have gone ahead and worked for me. However, it's not implemented, which was very confusing that they have documentation describing this. And then even when I did the nightly build of tfds, it was not implemented. So again, this didn't work. Here I tried doing the nightly build. I moved from 4.01, which is the current stable build of tfds, to 4.3. And it got further, but I got an error that I couldn't find any help on, so I wasn't able to work there either. So I decided, well, okay, I'll go back to the other method and I'll copy in, I'll clone the repository again, and I'll manually copy my dataset PI into the TensorFlow GitHub repo that I pulled down. So I did that, and lo and behold, now when I run the download and prepare, it actually gives me the nice familiar, pulling down the data set. Everything's working, training coming down, test data sets coming down. And I can do a standard tfds.load of my data set. And I can pull through and, examine the data set. The features, images are the size I expected. The label here is 0, which I can't remember. Maybe that's probably a horse. And then I can look at the info that when I pulled it, I used with info true. So I got the info data set as well. And I can look in there, and there's my data set. But it's Larry's data set Lawrence's data set that I reused, but it worked. So it's a lot of work to do this, but that's how you make a data set, and it's a TFDS data set that's local. The next thing to do would be to check in, the back into GitHub and then do a pull request. They do want you to write test. So you'll see, like, Lawrence has got his horses are humans here, and then he's got a test file that goes with it. So you also should do this. He's going to do things like, I'm not sure what he does. Yeah, so he gets kind of a pretend data set here with a small split. And I don't know he doesn't do too much, actually. I've seen some of them where they do quite a lot more testing on how so you might see, do some tests to see if you can do the splitting correctly, if it works with supervised keys or without the keys, things like that, to make sure everything's functional. And if everything goes well, the folks at Google will approve your data set to be added up into TensorFlow data sets for the public to use.
Cool. David, what was the difference here that worked? Wasn't it the same CLI command, same dash command that you executed in the other notebook, or is it different?
So the difference, yeah, there's a couple things I did differently. Were pretty similar, but
for the content, I know the content is different.
Yeah. So I don't know if it was exactly the content, but he used in his notebook from the course, he used, where is it? So he had to run a Python command to generate everything. I'm just trying to get back to it.
Oh, the initial.
All right, so here he used this script, right? He called from, so he had to download everything with GitHub, clone everything and get it down, and then run the create new database with your database name and the type you want. And that created all the stubs that you need to then go in and do this part, right?
Yep.
And what I did was I used that newer approach of
command line.
Yeah, command line. So if you look through their tutorial here, all you have to do is call the command line new in your database name. You edit the mydatabase.py file so that you have implemented those 3 methods, and then you can call build, and you're good to go. But build doesn't work. So unfortunately, I don't know what, I couldn't find anybody else that had the same error message. So what I did,
Yeah, what did you do?
what I did was a hybrid approach, right? So what I got to work was this one, which I did the build to build the stubs.
Oh, I see.
Excuse me. I used a command line with new,
Hmm.
build all the stubs. Then I just implemented everything in the same way that he implemented it for horses and humans. But then to actually get it deployed into TFDS, I used GitHub to pull down TFDS and then manually copied it over right here. So here I copied
Sure.
that file that I had altered. I copied it into
Right.
into
And
the,
that
into the
cell number 10, Python script download and prepare, is that the same between this notebook and the first notebook?
This is the same, yeah.
Okay, got it. Okay.
Yeah.
So CLI for initialization and copy an existing example, edit it a little bit, and then
I suspect I could have, I don't know, I'm not sure really what, I assume let's look real quick. I assume they still have that other one, the create new database is a script, is in the scripts.
yeah.
Let me see. Is it going to be?
So the TFDS new probably uses another version of
It's not there. Where is it?
script.
Yeah. Dataset scripts. Oh.
Yeah, TFDS scripts.
Yeah. Scripts what? Create. No, I don't see it. So maybe they've actually replaced it with it.
Is it under tools? No.
I can go back. Hold on. I have to look over here at this other one. So it was supposed to be scripts and then create new. Yeah. So the newer version, they've gotten rid of that. So I'm not sure if they expect you to use the command line or. I don't see anything that says create new. Let's see.
Yeah.
No.
I mean,
So,
TFDS new must use some kind of script in the back, and it's just not clear which one.
right.
New.
There's build.
There's new.
Yeah, this is new. So this is definitely what it's using, right?
Oh, I see.
So this may have replaced that other script. Yeah.
Hmm.
So maybe you could still run this directly. I don't know, but
Right.
yeah.
So CLI for init and Python for build and prepare.
Yeah. So I suspect, that they would give you lots of support because they're very interested in having you upload your database. So I think you can get a lot of support for this. So if you do run into issues when you're trying to do this. But I was, yeah, I don't know if anybody else tried the original collab or notebook that was in the course. Now this is where they stopped at the prepare, right?
Mm-hmm.
And I just wanted to see if it actually would run, but it didn't run. So yeah, they never ran this. So I tried it and it didn't. I never got it to work. I don't know if anybody else tried it.
I haven't tried it yet, but I'll let you know.
Yeah. I mean, it was interesting. I even I looked at it, said, oh, it's not in there. You must have meant to choose one of these, right? And so I even went into the I think it was here in the init, yeah. And I took out the first one, right? I just removed this line and thought, well, that'll tell it it's not there. And it still said I should have, that it should have been one of these, and it still listed abstract reasoning. So it's like it wasn't even looking here for some reason. Yeah. Which I was like, I'm not sure, is it looking back at online somewhere and it's not using my local one. So maybe this command doesn't work. I don't know. So
I like the path you took. The adventure you went.
right. But like I said, maybe there's a better way, and I think they would certainly give you lots of assistance. But all right, so that wrapped up that. I'll stop sharing unless there's a questions. No.
Yeah, I don't see any in the chat. Interesting. There's a lot to it, right? Basically you're like publishing something on the internet, so make sure that it follows the different standards that TF has.
Yeah, and they do a pretty extensive review of it before they approve it. So in their pull request.
Cool. So I think that concludes course 3. Is that true?
Yes.
Can't believe we did it.
The longest one yet.
3-4 weeks.
So what's the next course?
The next one is on Tensorboard, TF Hub, serving, TF serving,
privacy. Yeah.
privacy, preserving methods.
It's really more the deployment. Yeah. We deployed to browsers. We deployed to TensorFlow Lite scenarios,
Right.
edge phones and edge devices. And now we're going to look at deploying onto massive scaled
Cloud.
Cloud.
Supercomputers.
Right.
Which everyone has one now in their pocket.
Come full circle.
So in that environment, would you want to presume that you're running with Kubernetes, or, what exactly is the scope? I'm trying to understand of that next course. Is it just the TensorFlow tools or Google tools, or does it go?
No, it's within the TFX ecosystem. Yeah.
Right.
Yeah.
Thanks.
Cool. All right, David, appreciate it. I'll stop the recording here for YouTube, but I'll leave the floor open. For everyone who's joining us online, thank you so much. We'll be taking a break next week for happy hour, and then we'll resume the week after that with course 4. So thanks for joining us, and feel free to like and subscribe.
Thank you. Good night, guys.